and I'd like to thank everyone who's joining us today from Toronto, Germany, and around the world. And the way we're going to do this today is we're going to have a couple of slides explaining what this Optimum library is about that we've released recently, and also this Infinity product that we have at Hugging Face. And then we'll dive into some hands-on examples with 2 Jupyter notebooks that we'll share during the talk. And if you have any questions about anything that we're discussing, just post them in the chat, preferably with like a queue at the start so that we can read them and quickly find them. And yeah, with that, I reckon let's get started. So just a little bit about us. I'm Lewis. I'm a machine learning engineer in the open source team at Hugging Face, and I'm responsible for like maintaining the ONNX part of transformers. And I also build a lot of the infrastructure and backend around evaluating transformers on the hub. And I'm joined today by my colleague and friend Philipp, who's a tech lead at Hugging Face, and he works primarily on developing the cloud solutions that we have at Hugging Face. So you may have heard of the Amazon SageMaker deep learning containers we have. Philipp built those, and we also have some new kind of cloud initiatives that Philipp's leading. And he's also very passionate about democratizing machine learning and NLP. And he's also got a great set of blog posts about using transformers in all sorts of domains. So I recommend, if you haven't followed him yet on Twitter or read his blogs, go check it out. So the plan of attack for today is maybe just to remind ourselves like why we're here. I guess most people probably have heard about transformers and sort of are interested in understanding how they fit in the broader ecosystem at Hugging Face. So we'll kind of just cover briefly, just to remind ourselves what these 2 things are about. But the core focus today will be about the Optimum library, which is this new open source library for making transformers run fast, both in training and with inference. And also the Infinity product that we have, which is a packaged solution that lets you, scale transformers with very little, need to develop or code yourself. So I'd like to start with like a bit of a quiz. So what you can see in this this diagram or this picture is we've kind of got 4 products from 4 major companies. We have Tesla Autopilot, we've got Bing Search, we've got Google's Gmail autocomplete, and we've also got Facebook's kind of like recommendation system. And the kind of question I'd like you to think about is like, what do all of these kind of technologies have in common? So probably like the first thing that might come to mind is like, okay, these are all kind of like machine learning applications. We know that Autopilot, needs to ingest very different types of modalities of data and then use this to make decisions about lane changes and so on. We know that Google Autocomplete is doing some form of like, language modeling. And similarly for search and for recommender systems, we know there's some kind of ranking behind the scenes here happening. And the kind of thing that is kind of in common with these that we know from the sort of public releases that these companies make is that the underlying technology or the underlying sort of deep learning technology behind this is the transformer. So if you're just coming here and you've never heard of a transformer, in a nutshell, it's this diagram here. But this diagram is, of course, very complex and not necessarily easy to understand the first time you see it. So if I just want to describe what a transformer is, just in a very high level, I can just say it's a sort of special type of neural network that can very efficiently model sequential data. And so this is a kind of big breakthrough that was developed by Google in 2017. And it was primarily developed for natural language processing, and then quickly jumped into many other domains outside of NLP. And what these companies have been doing for the last few years is utilizing this kind of single type of network to improve all of their systems in rather dramatic ways. And so the sort of big question we've been kind of asking ourselves at Hugging Face is, how do we empower individuals and companies to use this very powerful technology for as many people as possible? So if you're sort of a machine learning engineer, either working on NLP or maybe in computer vision, the question we always ask is like, how can we make the simplest route from the release of these models to being able to apply them in your applications as smooth as possible? So the way we kind of do that is primarily around the Transformers library, which you may be familiar with, but also the Hugging Face Hub. And the Hugging Face Hub is the sort of platform that we have at Hugging Face, which combines both model repositories for machine learning model weights, but also data sets, because in order to train models, you need data. And we also have a feature called Spaces, which allows you to build interfaces to your machine learning models using very simple tools like Streamlit or Gradio. And I'm not going to talk so much about all these additional features. I think what's kind of interesting is just to focus on sort of some of the most relevant parts for today. So the sort of first part around the hub, as I was discussing, was that it kind of brings together all these different components. And if you haven't got an account, I recommend just going to huggingface.co, and you'll be able to then sign up, and then you'll be able to follow along with the notebooks that we're going to use today. And when you visit your page, you'll see some sort of activity about what's happening both in the community and the things that you've been working on. But the kind of sort of thing that we're trying to push for in part of our vision at Hugging Face is how to use not just the breakthroughs in transformers, but also the kind of broader breakthroughs that are happening in machine learning more generally across things like biochemistry, time series, reinforcement learning, and how can we kind of leverage this platform that we've developed initially for transformers, but for many different open source libraries and for many types of problems. So today our kind of core focus is roughly on these like 6 domains, but we're rapidly kind of expanding into other areas. And if there's some domain that you work on today that you don't think has great integration with the hub, please reach out to me or Philip after the talk, and we'd be very happy to discuss further. So as I was mentioning, the Hugging Face Hub is this platform where we have model repositories. And these model repositories, they combine various different elements that allow users of the hub to make decisions about whether they should use a particular model in application. So you can see here, we've got the GPT-2 model from OpenAI. And there's a model card on the left which describes what this model is about. It also lists some of the kind of biases that are in the model. And on the right-hand side, we have an interactive widget, which lets people very quickly, interact with the model, type some text, and kind of see, in this case, what type of generations you get. So what you can see is I gave the model, my name is Lewis, and I like to, XXX. And the model then completed this and, made up some kind of, hallucination that I call myself Nike, and I'm not an expert in tennis, and so on and so forth. So this is sort of like the way that we feel like, using machine learning models in the real world is not just about, taking a model and a data set and then training it, but it's also about this broader picture of interacting with the model and also documenting on model cards, both, how the model works, but also the some limitations in it. And if you look closely at this picture, you'll see that there's this like brand new community tab at the top of the model card. And this community tab is a feature that we launched just about 2 weeks ago. And this is now a feature on every single repository on the hub, so for models and data sets. And basically, we now enable the community to have discussions in the open about fixes on the models or improvements or any sort of issues they might have identified. But you can also open pull requests on the models, both as the owner of the repository, but in particular, if you see that maybe there's some field missing in the configuration or something like this, you can open a pull request to make a fix. And so this is a feature that we're really excited about because it's sort of like the first truly collaborative feature that we've built, which brings together the whole community to build a more robust and hopefully exciting platform for developing machine learning applications. And the kind of thing that maybe everyone here knows about is that Hugging Face is primarily an open source company. And so what this means is that many of the sort of technologies that are behind the success of our platform are really coming from open source libraries that people can just use for different applications. So of course there's the data sets and transformers libraries, which you probably know about from working as engineers or data scientists. But the one that we want to talk about today is the Optimum library. And with that, I'll let Philipp take over and tell us a little bit about what is Optimum, and also what is this Infinity product that we have at Hugging Face.
Thanks, Lewis. Yeah, so Optimum is really like a new open source library we built, but not like by ourselves. We build it together with our partners, in particular with hardware partners. Since we have this nice transformers library, which makes it super easy to run those models, we have a unified API to like train those models, run fast inference with the pipelines where you don't need to write pre or post processing, which is an easy way to get started. But to like really scale your training and inference, you often want to like make hardware optimized changes to either your model or to your training loop. And I think over the last 2-3 years, like the whole like chip market changed, with where we see more and more new optimized chips for machine learning. For example, GraphCore with their IPUs. We have now Habana with Gaudi and Goya. And then, of course, Intel with all of their new chips coming up, really making sure that we can like create or run fast inference on it. And Hugging Face Optimum is really like this centralized place for accelerated machine learning for training and inference for hardware-specific platforms. And of course, CPU and GPU are also hardware-specific. So we not only have like those nice features for IPUs and like Gaudi instances, we also have them for CPU and GPU leveraging, for example, Onyx runtime or the Intel Neuron compressor. And similar to Transformers, we provide a unified API which orients itself at Hugging Face. So in Transformers, so we have in Transformers this, maybe you're familiar with the trainer class, and for Optimum we have also the trainer class, but for our hardware-specific vendors. So for GraphCore, we have a GraphCore trainer, which is basically API agnostic to the trainer we have inside Transformers. Similar to Habana, we have a Gaudi trainer, which is agnostic to the trainer in PyTorch, meaning that you can like easily switch from your GPU-based training to your Gaudi-based or IPU-based training to get the best out of like both worlds and like benefit from hardware acceleration or saving costs by moving to a different underlying compute type. And as already mentioned, Optimum is like really built for inference and for training. Today we are going to focus on inference and specifically on graph optimization and quantization using the Onyx runtime in Optimum. And Onyx runtime is created by Microsoft, which is an open source inference runtime for running Onyx model. And Onyx, most of the, or like some people are often switching those. So Onyx is really a format for neural networks, and Onyx runtime is basically, as the name suggests, a runtime where those models are going to be run. So Onyx is really only the representation of our graph and of our weights, and Onyx runtime is the tool which we are going to use to run those models. And what we are going to do today is basically trying to use a fine-tuned model from the Hugging Face Hub, which was fine-tuned on the Banking 77 datasets, which is a text classification dataset with 77 classes around fintech data to classify intents based on customer chats and customer support. So the idea is you see it on the right, you have maybe some kind of customer interaction with questions on like, what is my balance? And then the classification model identifies this as correct as like for I want to know like what the balance is, and then you can run the API call and then respond back to your customer. And as a model which we're going to use a distributed model. And okay, here's the slide I was looking for. So as mentioned, Onyx is like an open standard for basically neural networks, meaning you can export models from PyTorch, TensorFlow, MXNet to Onyx, and then either use it as the Onyx format or like then convert it to a different framework. So Onyx is really only the representation of our neural networks. And combining those Onyx models with accelerators like Onyx Runtime or TensorRT, we can get really the best of both worlds. So we have like this unified graph representation, which we then can use with specialized accelerators to gain performance for running inference. And yeah, as mentioned, so like there are a couple of different ways you can optimize your model or make sure it runs faster. And like, for example, there's like knowledge distillation, where you are trying to like distill knowledge out of a bigger model into a smaller model. There are graph optimizations or quantizations and many more techniques like pruning or sparsity. Today, we are really going to focus on what Onyx Runtime is providing us with graph optimizations and quantizations. So if you have like more questions, idea about how to apply knowledge distillation or how could I prune my model using transformers, then like feel free to like create an issue in Optimum or like send us a message on Twitter, LinkedIn, or on our forum. So what are graph optimizations? So basically you can see on the right side, or in general, our neural network consists out of different operations, which are like run through when doing a forward path. And graph optimizations are basically methods and way to accelerate this forward path through our model by not like making any changes to the outcome. And the right side is basically an example for operation fusing, where we have a batch normalization and activation and a convolution. And the fused layer basically does the same computation, but in a more accelerated and more optimized way. And also other graph optimizations we could use. Constant folding is basically, okay, we are trying to find out if we have constant values inside our model and if we can like make them static, so that we don't need to like recompute them at runtime and like can do this in advance. And similar to redundant node elimination is like, okay, if we make one forward pass and see, okay, we have like different nodes in our model which are not used for inference, we are basically trying to like remove them, so we are not like having a lot of like any additional overhead in terms of memory or compute. And then the second part, which we are going to focus mostly, is quantization. And quantization, maybe a few of you have heard about it, is the idea is to move from a high precision data type to a low precision data type, since low precision calculations are faster and need less memory. So the idea is we have our neural network with float 42 precision values, and we want to like make it faster and smaller by moving from float 32 to int 8. And this comes, of course, with challenges, since like int 8 is like normally only like from minus 128 to 128 values we can represent, and with float 42 we can like, I think like, I don't know how big the number space is, but it's way bigger than for int 8. And the idea is to map our floating values we have fine-tuned inside our model to those int 8 values by using, I would say, clever calculations. So the formula you can see at the bottom is basically the whole idea about quantization. Of course, we like try to keep it pretty simple. For example, for the scale value, you can see on the right, you have like different formulas depending on if you are quantizing your activations or your weight. But in general, the idea is we have a real value represented as float 32, and we want to create with those formula an int 8 value, which we can use inside our model to gate the same output as with the real value. And the 0 point in this example is not 0, as we might know. It's basically a value we need to define, which can be used to create the real value 0. So if our real value is 0, for example, if we have padding or in convolutional networks, then our int 8 value and the scale together need to create 0 again. So for example, we could use as 0.128, and then when our int 8 value is also 128, and we have like 0 multiplied by something, which again creates the real value 0. But of course, it's like not always 128. It's really what the Onyx toolkit is going to like calculate for us at the end. But that's basically the whole idea of moving from high precision numbers to low precision numbers to save memory and have faster compute.
Can I ask some questions, Philip?
Sure.
So these are maybe not questions about quantization per se, but more about the broader picture of Optimum. So one question from Nauman is there a pairing of Optimum with the AWS services like SageMaker? Because it seems that ONNX or ONNX runtime is a pairing with Microsoft.
No, so Optimum isn't like really something mapped to something. It's really the idea is to have like an open source unified API to use different providers. So we are going to use ONNX runtime today, which is maintained by Microsoft, but Optimum also currently supports Intel Neural compressor, which is maintained by Intel. And then we have support for GraphCore and for Habana Gaudi. So the idea is really to create a toolkit which is not limited to a specific accelerator and provides a unified API. So you can like switch across different processors or across different hardwares to make it super easy for you to get basically the best like tool for your use case.
Awesome. And we've got now a question about quantization, so more to the point, from Nicholas, who asks, quantization is a destructive process though. The results might differ before and after the quantization. Do you want to sort of comment on that a bit?
Yeah, sure. So we're going to see it like in the hands-on session we're going to do later. And yes, you are right. So with quantization, you are never going to get like the same output as before. And accuracy always like, yeah, has a small penalty when going with quantization. So the idea for quantization is to, okay, I want to make my model faster and keep the highest possible like accuracy. If we could achieve the same accuracy with like just decreasing the model size without like any complicated changes, then I think it should be the default. But depending on like which quantization strategy you will do, as on the slide, we have like dynamic quantization, static quantization, and quantize-aware training. You will have different like penalties or loss in terms of accuracy. I think those will like be more clear in like the examples we are going to do, and you will see like hands-on how much of accuracy drop we are going to get basically by doing dynamic quantization and static quantization. But the idea is really, okay, I want to either make my model a lot faster and save compute costs by it, or to enable new use cases because my latency is now in a range where I can use it for my business use case. And I'm okay with sacrificing maybe 1% in terms of accuracy.
Awesome, thanks.
Okay, then I will shortly continue and then we can answer the remaining questions before we get into the hands-on test. As quickly mentioned, so quantization, or we have different ways of quantization. So the easiest one, which we are going to start later, is dynamic quantization, which basically means we are doing all of this like calculation you have seen 2 slides before on the fly, meaning we have inside our model or in our model graph those dynamic quantization layer, which will get in the like during the forward path, we'll do like the calculation between like float 42 and float 8 to have like a small like operation inside our notebook, inside our model, which is using int 8 values instead of the float 32 model, which gain there of course performance improvements. So the latency will be decreased, and it's like the easiest way to not lose accuracy, since we are like not doing any calibration or like changing the weights and activations inside our model. Then the other or another way of quantization is static quantization. That's going to be the second example which we are going to do. And for static quantization, we are doing like some kind of ahead of inference computation, where we are going to use our fine-tuned data set as some kind of tuning data set to calculate calibrations, which we are then going to use to quantize our model. So at the end, after static quantization, we really have those quantized values inside our model. In general, it gives better latency because we like don't need to do like this additional dynamic step, but it's way more complex to do, and also depending on how much time and effort you put into, you can get better accuracy or not. And then the last method is quantize-aware training. That's basically done while fine-tuning your model. So in our sessions, we are going to use an already fine-tuned model, which we like post training quantize, and for quantize-aware training, you are doing is during quantization. And as you said on the slide, so we are going to simulate the quantization during training with fake float 32 values. This means that we are not using int8 values. We are still using float 32 models, but we are rounding them to like full numbers, basically, to trick the loss to make sure we can only use our full numbers to then like easily quantize afterwards, because we still have like the float 32 number space, but the numbers are int8 numbers, which makes it super easy to quantize afterwards without any calibration. Okay, and then quickly before we go into our sessions, so all of what we said so far is like open source, available inside Optimum. We have a few examples and we are trying to make more examples. We have a nice documentation and getting started, guys. But sometimes open source is not enough for your company or for your use case, and you need dedicated support for SLAs to make sure that you can like deploy your model into production. And if something happens, there's like some kind of person you can get in touch to. And that's where we built a Hugging Face Infinity, which is really plug and play of all you have seen. We are not like only doing graph optimizations and quantization. We are like extending like the ways to accelerate your model even more. And Infinity comes as a containerized solution, which you can like deploy anywhere where container can run. And you have an inference container and like this optimizations container, which you can like use inside your environment to first optimize your model and then easily deploy your models. And we are currently seeing down to 1 millisecond latency on GPU for bird-like models, and up to 4 millisecond latency on CPU for bird-like models. And the whole like idea about Infinity was to build on top of open source, but for enterprises, meaning we have security checks all of the time. We make sure that we don't have like any compliance issues with how we run the models. We make sure licensing of the model is always correct, and that you basically have a dedicated support in case you run into any issues. And so far, Infinity was a paid solution, but we are planning to make it free for Hugging Face inference endpoints. So Hugging Face inference endpoint is a small teaser, something we are going to launch hopefully by summer as an extension to our inference API, where you can run Infinity and Infinity optimizations for free as endpoints, meaning that you can pick a model from the Hugging Face hub, say you want to use Infinity for it, and then it's hosted for you in an accelerated way, and you still like benefit from all of those enterprise features we have built into Infinity before. Okay. More questions?
Yeah, so we have sort of two questions, which I think we can also discuss a bit in the hands-on sessions. But one from Eugene is, you talked about quantizing from like, floating point precision to 8-bit integer. Why not go all the way to like, 2-bit integer? Or, does this just destroy the accuracy of the model?
Yeah, so something we already see with 8-bit integer is that's like, so you are like quite limited in like what numbers you can represent. And machine learning models are not like that simple that you can say, okay, like my weight for like my layer 1 is like 1, and then I have 2 and 3, and that's it. That would be, I would say, not like enough. And I believe like hardware vendors are like researching on how we could like go down to int4 or even lower. I know NVIDIA with their new Hopper architectures is working on having int4 support for quantization, but in general, it's just that the number space is not big enough to like match all, or like to calculate all of our like weights we would need for our networks to achieve any good performance.
Great. And we have a kind of follow-up question to that, which is the quantization process, or let's say the drop in accuracy, is that affected if you have different types of activation functions? So you can imagine that like I use ReLU, but then, some other part of the model is using GELU.
Yeah, so We will see it later. I hope at least we will see. So for the quantization, you're not saying I'm going to quantize all of my operation inside my model. Like some works better than the other one. And for in terms of activation, depending on like which framework you're going to use to quantize your model, there are different operations which are supported. So for example, for Onyx runtime, there's at least ReLU support, which I'm aware of. For the others, I'm not sure. So it's basically you want to export your model as an Onyx graph or maybe trace as torch script, and then like check your like nodes or operations which you're going to use. Check, okay, which operations are supported by the toolkit you want to use, and then you can see, okay, which operations or node inside my model can be quantized or not. And normally, like the most common operations you are quantizing is the matmul and the add operator, since those are like tend to be like the slower ones, since with mat we will be doing a lot of like matrix multiplication, which is like the bottleneck of transformers latency. So that's basically the idea where we would like to optimize the most and to get like the most or best performance out of it.
Yeah, and I think that actually also addresses a little bit the question from Nabila, who's asking about, what's the process to update operators for Onyx runtime? So if you've got something like layer norm, which is maybe not defined as a dedicated operator in Onyx runtime, can you do anything about that in Optimum? And I guess the answer for that is, well, not yet. I mean, we really just use Onyx runtime as the sort of backbone, and then we build on top of it to build the kind of transformers experience.
Yeah, so in terms of, so when doing quantization, it's not really that we like keep the original operator for like, let's stick with matmul. We are not keeping like the original like operator from Onyx or like from PyTorch inside. It's going to be basically replaced with a quantized version of it with the formula we have seen a few slides before. So it's really you are replacing the operators inside your model to be able to use those int8 values, and you can only like use operators which have compatible quantized available. Of course, you can like say, okay, I need to optimize my model even further, and I'm an expert in C and C++. Then you could like create or write your own quantized or optimized operator. That's where I hope Microsoft keeps up the good work to provide us like all of the important operators. But yeah, you can like, since everything is open source, you could of course like create your own operators, but it's like not as trivial as we might think. And then maybe to quickly answer Sovik's questions about which transformers model we can use before we get started. So for quantization, we currently support encoder models like BERT, Albert, Distelbert, Roberta, XLM Roberta, and also decoder models like GPT. We are currently working on having a way to export sequence-to-sequence models like T5 to Onyx. But when doing this, you are not getting like one Onyx file. So currently, when you convert normal transformers like BERT to Onyx, you will get like one Onyx file out of it with our graph. Same for decoder for GPT. When we export it, we have like one Onyx file. And for our sequence-to-sequence models, we are getting two files. So we will end up at the end with an encoder Onyx and a decoder Onyx. And then once we have like this feature enabled, we could go ahead and quantize the encoder and then also quantize the decoder. But this might take a few more weeks or months, since like the whole like calibration and evaluation takes longer, since the inputs for encoder are harder to compare to like what we currently have in PyTorch, since you basically have split up the model into two separate ones. But we are like working on adding support for all, I would say, architectures type, which are supported by operators for Onyx runtime. Okay. Let's do some quantization.
Yeah, let's write some code. Okay, so I'll share my screen now. Can you see this, Philip?
Yes.
Great. Okay, so for everyone who's following online, we have a repository under Hugging Face called Workshops, and I'll just chuck this quickly in the chat. And in here we have a folder called MLOps World, and we have two notebooks that we're going to look at today. We have one on dynamic quantization and one on static quantization. And if you click on one of these, you'll then see a little Colab link, which will run the code. But if you want to get like the kind of results that we're going to talk about today, you're really going to want to be running this on some sort of dedicated instance, like a C6 large or something on AWS. So this is just if you want to follow along. And I'm going to sort of get started by talking about dynamic quantization. And this is kind of like, as Philipp explained in his talk, it's the sort of like simplest type of quantization one can apply, because you sort of just do it at runtime. And generally speaking, it will give you like a kind of boost in your latency with a relatively minor impact on your accuracy or whatever metric you're doing. And it kind of doesn't really cost you much in terms of code. So the kind of advice that we give is like, start with dynamic quantization because it's kind of simple. But if you really need to like squeeze out a bit of extra performance and you don't want to have a big drop in accuracy, then you should really go for the static quantization process, which Philipp will show us shortly afterwards. And yeah, if you let me know if this isn't zoomed in enough, and we can make it bigger. Okay, so what we're going to do in this notebook is we're going to obviously look at the Optimum library. And we're also going to look at a brand new library that we've released at Hugging Face called Evaluate. And this library has been developed to kind of simplify the way that we evaluate and compare models more generally, not just transformers, but more generally in the Hugging Face ecosystem. And so we're going to be looking at some of the sort of nice features that this library provides. And what we're going to do is we're going to start with a model that we've fine-tuned on this banking 77 dataset. And this model is a distilled BERT model. And you can see that in the model card on the sort of validation set, it got around an accuracy of around 92.5%. And if we, compute some of the predictions from the model, we'll get a taste of like, what the outputs look like. So here I'm providing it with a kind of typical query that someone might ask about, a banking application, why my top up wouldn't go through. And, the hub is or the inference API is going to load this, and then it's going to provide us with predictions. And so you can see that, it's banking 77, which means we have 77 different classes to deal with. And through these, we'll see, okay, the sort of most probable prediction from the model is, this should be a top up by cache or check intent, which would then be mapped into some sort of like, canned response by the digital assistant. And the other thing that's like maybe interesting to mention on the hub is that a lot of the time you can actually see the evaluation results down in the sort of model page itself. And we also have a link to Papers with Code. So Papers with Code is this great website which collects like kind of evaluations and data sets across many different domains. And there's a little leaderboard that is, being populated for this data set. And you can kind of see, here's the model that we've trained. Okay, so let's get started. The first thing that you'll need to do if you're running this on your instance or in Colab is install some dependencies. The main thing to notice is that this MKL include an MKL dependency. This is something that is designed specifically for a certain class of Intel chips to sort of squeeze out the performance of like, the mathematical operations like matmols that we're going to do. So if you're running this on Colab, you'll just want to get rid of those two dependencies. And inside Optimum, the way that you install the different kind of backbones is by specifying the type of extras that you're interested in. So if we were trying to, for example, train transformers on an IPU from GraphCore, we would just replace this Onyx runtime extra with a GraphCore extra. And then this would install all the additional dependencies that one needs for IPUs, and so on and so forth for Habana and also for the Intel neural compressor. And for dynamic quantization, we can run inference on GPU for certain classes of operators. And so if you also want to, compare what happens in that case, you just have to include this GPU set of extras. So what we're going to do to get started is we're just going to turn off some warnings and things that happen with the tokenizer. This is just a sort of setup. And the first thing that I'd like to show is kind of like what the process looks like now that you've got your fine-tuned PyTorch model in the hub. How do we go from this process of exporting it into the ONNX format and then optimizing that ONNX model with techniques like dynamic and static quantization? So the main thing that we have in Optimum is that we have essentially the same kind of classes that you might be familiar with in transformers. So in transformers, we have these auto classes, which are usually associated with a different type of head. So for example, you'll have an auto model for sequence classification, which is suitable for transformers like BERT, which have been fine-tuned on classification tasks. But you might also have an auto model for, I don't know, causal language modeling, which is then, the kind of class that you would use to load GPT-2. So in Optimum, we have a dedicated set of classes which are designed for ONNX runtime. That's what the ORT denotes here. And the process is very similar. We specify just the model ID on the hub. And we specify that we're going to load this as a transformer model. And what this is going to do under the hood is when we run this bit of code, it's going to download the model from the hub, and then behind the scenes, it's going to convert those set of PyTorch weights into the ONNX format. And so now that you have this ONNX model, we can, for example, just try to see, can we do inference with it? And until recently, the way you had to do that was really like a kind of pain in the neck. You had to take the model, you had to kind of spin up like a sort of inference session with ONNX runtime. You then had to, feed in like your NumPy inputs into that inference session, get the outputs, and do all the kind of post-processing yourself. And one really cool feature that Philipp implemented is the idea that we can essentially take these ONNX runtime models in Optimum, and we can just feed them straight into the transformers pipeline. So if you're familiar with this pipeline function for transformers, you basically specify a task, a model, and a tokenizer. And then this will automatically take care of all of the pre and post-processing steps that convert your raw text into tokens, into input IDs, feed them through the model, and then ultimately you'll get now some logits, which are then, aggregated to compute things like, the probabilities. So if we run that now with this this ONNX runtime model, or this ONNX model, you can see that the pipeline has predicted that, for this query, the most probable intent is lost or stolen card, which makes sense. And I hope you can kind of appreciate that this is quite cool. We're running an ONNX model through a pipeline in transformers, which means that, you no longer have to really worry so much about, the actual ONNX format, which is, for me, I think, very cool. So this is what we call the vanilla classifier. This is our kind of baseline model. This is the thing that we fine-tuned and we want to optimize and we want to compare against. So what we're going to do in our first step is we're going to save this model to disk along with a tokenizer. And then we're going to use these outputs as inputs into our optimizer. So what I have to find up here is an ONNX path where we're going to save all of these outputs, all these files. And if we have a look at them, you can see that, I've got the kind of usual things that I get from saving a tokenizer. I've got like, the vocab and so on. And then I've got these two extra files which are coming from Optimum. So we've got the ONNX model, which is essentially this computational graph that Philipp showed us. And we've also got a config.json file, which is analogous to the config.json file you have in transformers, which will indicate like what kind of architecture basically defines this model. It will also tell us, for example, what are the label mappings associated with this model, which is important when you want to make sure that the predictions of your model line up with the data set. Okay, so are there any questions at this stage, Philip?
The only question came in by Chris was, can the pipeline accept the list of inputs?
Yes. So, for example, I can do something like this. You know, I've lost my PIN number, something like that. And now if we feed this, it will, you know, process them, you know, and in this case, it's just doing it on the CPU. So it's just going to process them kind of sequentially, but you can also do GPU batch processing if you use the GPU part of Onyx Runtime. Great question. Okay, so we've got this model. It's in the pipeline. Now we want to, you know, optimize it. So the way that you do this in Optimum, there's kind of like three main steps that you're going to follow, both roughly in this example and also in the one that Philipp is going to show us. So Optimum is based around this idea of having different types of quantizers and optimizers. And these are things that you just sort of instantiate, kind of similar to like, you know, a configuration that you would do in transformers. And that's also what we do here when you sort of specify, okay, I've got a quantizer, like a generic quantizer, but now I want to specify, you know, is it dynamic, is it static, you know, what type of operators I want to, you know, quantize. And then the final step is to kind of take this Onyx model that we started off with, you know, apply the optimizations and then export the result as a new Onyx model, which we can then, you know, run inference with. So the way this works in practice is we just import, in this case, a quantizer and a quantization config. And what I'm going to do is I'm going to create or instantiate a quantizer using the from pre-train method. And this is, you know, the same kind of like API that you might be familiar with from transformers. And the idea here is this is going to take, you know, the model ID that we defined at the start. This is the model in the hub. And we also need to specify the kind of task that we're optimizing for. And so because this is like a model with a sequence classification head, the task is, you know, naturally sequence classification. And so once we've got a quantizer, the other ingredient we need to specify is a kind of configuration object, which is very similar to like the configuration objects in transformers, but now designed for quantization. And this auto, oops, I haven't found it yet, so let's just run this. This auto quantization config, it has a different set of methods for different types of instruction sets, or essentially kind of hardware that you're running on. So you can see that in this example, we've kind of picked this Intel AVX 512 kind of CPU instruction set. But if you're running on like TensorRT or, you know, ARM64, then you would obviously pick, you know, the kind of appropriate instruction set that you want to optimize with. So what I'm doing here is I'm specifying that my config is going to be dynamic. So is static is false. And I'm also specifying that I don't want to optimize like kind of every single channel in my graph. And that's just a sort of technical reason with dynamic quantization where you typically just want to optimize, as Philipp mentioned, you know, the certain set of operators like the map moles and the activations. So we set that to false. And then we just run dynamic quantizer.export, and we have to specify the path of our kind of source Onyx model. So this is what we're starting with. And then we also specify the output path, and that's going to now be called model quantizer.onyx. And we also provide the config. And when we run that, the output of this will be now a path which tells us where our model lives. So we can see it's in this Onyx folder. And indeed, if we look inside that folder, we now see that in addition to the model.onyx file that we started with, we've now acquired a new model called model quantized.onyx. So this is now the sort of dynamically quantized model. And what we can do just to sort of get a taste of what's happened is because we've reduce the weights from, you know, FP32 to int8, you would expect that there will be a reduction in the sort of size of the model on disk. And indeed, if we run this, we can see that the original model took around 255 megabytes of storage, whereas the quantized model has roughly been reduced by half. So even though we went from FP32 to int8, you might sort of expect, okay, why isn't it a factor of 4? But as we discussed previously, you don't really quantize every single part of the model, right? You don't quantize every single parameter of your transformer. We're only sort of selectively quantizing kind of like so the layers, and so this gives us roughly a reduction of 2 instead of 4. Are there any questions?
Yes. So maybe like one thing you could share again. Maybe it got lost. So Lewis ran the dynamic quantization like while explaining all of this. So it really took only like a few seconds. Maybe you can like show it again. So and then a question from Nabila came in. Can we just reuse model.onyx quantized with the old inference session / ORT way and pass it to the optimum for quantization step? So I think if I understand the question correctly, Nabila, maybe you can like add a comment on it. So you already have an exported model.onyx for a transformer model, and you would like to use the ORT quantizer to now like dynamically or statically quantize your model. Yeah, okay, correctly. Yeah. So Lewis, can we like use an already existing exported model.onyx with the ORT quantizer currently?
Yes. So I think that's explained in this part of the export line, right? So the main sort of thing we need to give to the exporter is the source model. So this is this model.onyx file. This is the completely, vanilla model that's been exported. And then that will be fed into the exporter, which will then apply the quantization techniques. And then the output will now be this quantized model. So you can certainly do it. I don't know if there's a sort of different thing you had in mind, Philip?
Yeah. So maybe one thing I can add. So in the line where we create this ORT quantizer, we currently like use the from pre-trained method with our model ID from the hub. And what this does, it's also loading a tokenizer and like the config JSON we have exported to know, okay, like which model architecture we are going to use, like what's the number of heads, how many or what's the hidden dimension, like those kind of values are needed to like efficiently like quantize and optimize the model. But you can like also create the ORT quantizer without the from pre-trained method and provide the information for your model. But I guess the easier step is if you have your model as like a PyTorch model and then like would like to like export, quantize, optimize, to go with like these steps Lewis has shown. If that's not possible, or maybe if you have like some different changes, like different heads or like different outputs, then you need to create like this ORT quantizer instance by yourself to make sure that we have like the correct feature. But we have heard this request now a couple of times and definitely are going to invest in to make it easier to use like the API, as we have seen with already exported models to dynamically quantize or optimize them with the same API.
Awesome. Thanks for the clarifications. And indeed, as you can see, it took around, 6.5 seconds to do the quantization process, which is, not too bad.
Yeah, and then two other questions came in. Mm-hmm. Can we save the quantized model in TensorFlow saved model format?
That's a good question. I think the short answer is no. So what we can do is we can save it in the Onyx format, and then we could use something like TF to Onyx, or there's this kind of converter that will map the Onyx model to TensorFlow.
Yeah, I think this is something we need to be very careful. So Onyx is like this like global representation standard, where you can like go from PyTorch to Onyx and then to TensorFlow. What we have done in the example here is now we already replaced some operations inside. So the model operations and the ops we have in the model are not like the standard ones. So for the quantization, we added like Onyx runtime specific operators, which are created by Microsoft. So if we would like to like convert our new dynamic quantized model to a different framework, it might not be possible because we like don't have like compatible other operators in TensorFlow to like use like this dynamic quantized linear layer, for example. But what I know is like instead of using Onyx runtime for a dynamic quantization, TensorFlow offers with TF Flight similar features to like dynamically quantize your models. So that's definitely possible. And then maybe like to quickly answer Noman's question. So currently we only have support for static and dynamic quantization, but our team is working on quantized aware training with PyTorch and TorchFX.
And also Onyx runtime.
Okay, that's even better.
Yeah. Yeah, so yeah, just to add a little comment on that, like in the Onyx runtime universe, the way that you think about things is that you've kind of got this idea of like a front end, which will be like, say, PyTorch or TensorFlow. That's usually the thing that you train the model in, or the framework that you train the model in. And then you will have this intermediate representation. So this is now the Onyx part that Philipp was emphasizing. And once you have that intermediate representation, then you want to think about, okay, what accelerator do I run that representation on? And this could be, you know, Onyx runtime, but it could also be, you know, something else. It doesn't have to just be Onyx runtime. There are different types of accelerators that will also ingest an Onyx model and, you know, apply their own types of optimizations on. So just to keep in your head, it's like PyTorch TensorFlow to Onyx, and then Onyx to accelerator. And currently we support, you know, PyTorch models for the exports. But in general, I think, you know, once you get your model into this Onyx format, you can then, you know, apply many of these optimizations directly on it.
Mm-hmm. And then like Benjamin asked the question, like all of this sounds super positive. Are there like any downsides to Optimum or optimizing a model? I guess that's where we like can now continue with the results of what we have done.
Exactly. So that's a great question. I'm going to talk about, you know, what the kind of drawbacks that happen with model performance when you do this. But before I do that, I just want to show you quickly that it's relatively simple to then take our quantized model and then feed it into the pipeline. So in the same way we did before, we're now going to load the optimized model using the from pre-train method. But instead of, you know, pulling this now from, you know, some hub or something like this, we're going to specify the local directory, and we're going to specify, you know, load me the quantized model. And then we just take the same tokenizer as before. And when I run this, the cool thing is that, you know, I just fed in this quantized model into the transformers pipeline. And indeed, I now get, you know, the kind of expected intent for this query. So this is kind of a sanity check that, you know, the quantized pipeline is also working as we expect. So to answer Ben's question, we want to now, like, a really important thing when you do any sort of optimization, it doesn't matter if it's dynamic quantization, static quantization, graph optimization, you know, whatever. What a lot of people seem to do the first time they do this is they go, oh, wow, it's like way faster. But you should really check that your model metrics, you know, haven't been affected too much. And this can, you know, be quite dramatic in some cases. So what I'm going to show here is a kind of API that you know, we find quite useful for evaluating models. So inside this evaluate library, we have an evaluator. And this evaluator is kind of similar to the pipeline function from transformers in the sense that you specify the kind of task that you're interested in. And we need to provide this evaluator with a data set that we want to you know, score our model on. So I'm picking the test data set of banking 77, which our model has never seen. And I also need to provide a label mapping because with text classification problems, you need to know, like, okay, how do I map the string that, you know, denotes the intent, you know, lost card, to the ID that, you know, ultimately the model is using for the scoring. And if you kind of have a misalignment between the model's internal mapping and the data set's mapping, then you're going to get very, you know, nonsense results because they'll just, you know, won't line up, and you'll basically just get, you know, very, very low accuracies. So that's just a sort of technical detail that we need to do just for text classification. And then the way this works is you run a compute method. We provide a pipeline. So here we're passing the quantized pipeline. We pass the data set, we select the metric, and then we just need to say, okay, what are the columns of my data set that correspond to the inputs and labels? And then the strategy is just an argument, which in this case will just compute, you know, just the accuracy. But if you want to have something like bootstrap sampling, you can feed that as a choice in the strategy argument, and then this will compute like the confidence intervals, for your evaluation, which personally I think is really cool because, in machine learning, we often just go, here's my result done. But what is, really interesting is to know, what is the spread of that result. So if I'm comparing models, are they statistically different in terms of their, performance gains? Okay, so here you can see that the model got 92.43% accuracy, and the original model, as was quoted in the model card, is 92.5. So you can see that we've, lost, a small amount of accuracy, and this is like, one of the things of like the drawbacks. So you're almost always going to have a hit in your accuracy or whatever metric you're optimizing for. And the amount of hit you get will kind of depend on the type of architecture you're dealing with. So for like encoder-based models like BERT, RoBERTa, and so on, generally speaking, we see that the drop isn't so large. But if you're doing something like text generation, it's a little bit more subtle because you're generating like, many generations, and each generation may have a bit of noise introduced through the quantization process. And so if you're doing something like beam search, at the end of your search, you may find that the sort of output generation is somehow of a lower quality than you would have gotten if you had just done, the vanilla model. So these are kind of like the main drawbacks that you see with quantization. But in general, I think it's almost always worth trying it because it only takes, a few seconds to minutes to try, and it almost always gives you a boost at small cost. Okay, so now what I want to do, just to wrap up this section, is we've seen that, okay, the model is getting a pretty good score of accuracy. Now let's compare, how do the latencies measure up? So we're going to provide it with a kind of payload, which has a fixed number of tokens. And what this means is like we're going to give, repeatedly the pipeline, both for the original model and the quantized model, a fixed sequence length. And it's generally a good idea when you're benchmarking your models is to look at, how they perform or how the latency evolves as you go from different sequence lengths. So you might start with like a sequence length of 8, 16, 32, 64, 128. And then you can sort of see that, depending on your use case, where the model is kind of, maybe struggling with latency and where you should maybe think about, some additional optimizations. So we've implemented a little function here that basically computes the latency, and it just iterates over the pipeline with this payload a number of times. So if I run this, it's going to first compute the latencies associated with the vanilla model that we started with. It's going to do the same thing for the quantized model. And then at the end of this, we'll see what kind of improvement that we got, through this quantization process. And generally speaking, you'll see the kind of absolute numbers that we're looking at will depend on what type of hardware you're running on. So here we're running on this C6X large instance on AWS. And if you're running in Colab, you might get different numbers just because they have a sort of different CPU in the back end. So you can see here that in the sort of 95th percentile of latency. So, latency has a distribution, and, it's good to look at both, your average case latency, but also looking at the 95th percentiles, because those are the ones that you really care about. You want to make sure your model, if you have some SLA, you want to make sure that, your model can meet that SLA, 95% of the time. And so you can see here that the vanilla model had a kind of latency of around 65 milliseconds, and the quantized model is around 37 milliseconds. So this gives us a gain of around, 1.8, which again, it might not sound like much, but if you think about scaling this, imagine that, you're computing, 1 million requests, per day or something like this, then, reducing the time it takes to process those requests means, you don't have to run, for as long on the instance that you're using, or you can then, scale out, more cost effectively. So that's pretty cool.
Maybe something to add. So the slide shows here like 1.9x. Lewis has now seen 1.7x. So that's a very like basic kind of benchmark. So we are like just looping over it in Python. We are running on the same machine with like the CPU cores like not fixed, meaning so our model is going to use the CPU, which is cores which are available. So if you like really want to make a more like precise benchmark, it's definitely recommended to like really think about, okay, pinning the number of CPU cores for like Onyx runtime or also for PyTorch or TensorFlow to really get like those static values in terms of performance. Because like, for example, if now like the machine Lewis is running on is doing some kind of background job, or like the Jupyter notebook is saving something, then like the result could like differ even like by 50% or something.
Exactly. And I think even in the Onyx runtime repo, they also have some kind of like, guidelines of, what you should really pin when you're doing this. Okay, so that's, roughly, visually what we're looking at. And you can see that, for almost no loss in accuracy, we were able to get a decent reduction. But, this is like the first thing, right? You've got something now locally, and what you want to do now is ultimately, share that somewhere that you can then reuse for deployment. And so one of the sort of nice features of these Onyx runtime model classes is they also have a push to hub method. So this push to hub method is, familiar if you use transformers. And the way you use it is quite simple. You just need to have an account on Hugging Face and paste in an access token. And you can get your access tokens by looking at your settings. And then here there'll be an access tokens. You can, pick one of these that you create. You feed it into this little widget, and then it will log you in. And what you need to do to push to the hub is you just need to create a local repository or local directory that we're going to call the Onyx Hub repo. You need to specify what is the name of the repository you want to push to. And you need to specify, what is the file name that we wish to use when we load our model and push it to the hub. So you can see here, I'm basically just using those specific things to save both the model into this local directory and the tokenizer. And then you just run push to hub and you specify, okay, what's my local directory? Where's the target I want to push to? And to use the authentication token, so it associates this repository with my username. And if you do that, you'll get a model repo that looks like a little bit like this. Oh, no, it doesn't. We're going to get a model repo that looks like, one sec. This. So here we have the quantized model repo. And Philip and I have filled out the model card manually, but one thing that we plan to work on is kind of auto-generating these model cards. But here, we have some results, where it comes from, what the accuracies were, and you can also, interact with this model using the inference API. So that's now on the hub. And so then, if we wanted to use this in some deployment setting, I can then just load the model directly by specifying the repo ID and then feed it into the pipeline just as we did before. And voila, we've now reproduced, this little example that we did. So I hope that's given you a kind of taste of the whole process, going from loading a vanilla model from the hub, quantizing it, evaluating its performance, and then finally pushing it to the hub again. And with that, I think, are there any questions before we segue to static?
Yes, I hope like Benjamin, your question got asked. Like he asked like in the beginning, so do I need a check basically, or could I like put it into my pipeline and like always automatically quantize and then deploy my model? I think like Lewis explained it pretty well, that you should definitely have some checks. I mean, like those checks can be automated, and as Lewis has showed, you can like have your vanilla model like optimize it and then push it back to the hub to then like reuse it. So those kind of workflows can be easily implemented with the Hugging Face hub, and then like always like use the optimized repository to deploy. And then like Chris asked a question, I guess it's kind of similar to what Nicolas asked, is like how much more saving would we expect on a GPU, and also what should we expect for like I guess less dramatic quantization from float 32 to float 60?
Good questions. So in my experience on the GPU, you'll see roughly a similar factor, except that, as in, a factor of, like, say, 2x-ish. But of course, the absolute gains will be higher because, the GPU inference will be faster than the CPU by kind of definition. So if you need to go really fast, what you really want to do is run on a GPU with dynamic quantization.
Maybe something to add. So currently what we have shown with Onyx runtime dynamic quantization only works for CPUs. If you would like to quantize your model from float 32 to int8, you need to go with TensorRT, which has these capabilities for the new NVIDIA GPUs. But if you would like to stick with what we have shown, you can instead of do dynamic quantization, do basically, or convert your float 32 models to float 16, which also means we are reducing the number space, but we are keeping the float 32 operations, but just with our float 16 values inside the model, which reduces again size and also accelerates compute, and the loss shouldn't be that dramatic. And as Louis said, it's something around hopefully not more than 1% accuracy loss, and then 1.5 to 2% latency gains. But there's sadly no one rule fits all solution. It really depends on your sequence lengths, your model architecture, and your data set.
Exactly. And also crucially, whether you need to batch requests, right? I mean, if that's something that's important for your use case, then a GPU is a good choice.
All right.
Shall we now look at okay, the use case Philipp is going to say is okay, cool, dynamic quantization worked, but maybe we're not super happy about that, whatever it was, 0.07 drop. So the question is, can we squeeze a little bit more accuracy out of the model?
Yeah, I mean, so it isn't not squeezing out accuracy, it's more squeezing out performance. So Louis has showed, I mean, if we really quickly walk through the example, it takes maybe 5 minutes to go from a vanilla model to a dynamically quantized model. And we achieved almost 2% gains in latency and had a little less than 0 point something loss in performance. And when using static quantization, you will definitely see more benefits in terms of latency, as shown as here, but we will also see more or potentially more loss in performance. So for dynamic quantization, we are basically doing everything on the fly, which has the issue that we are doing some more heavy compute compared to static quantization, but we are basically gaining the best performance out of it. And for static quantization compared to dynamic, we are doing this in advance. So we are calculating these ranges and values, which we later use for our quantized operators, and then applying them during inference, meaning depending on the values we use to calibrate those ranges, those depend our model performance. And the model performance for a static quantized model can only be as good as for the dynamic quantized model. So normally, if you dynamically quantize and you get 99.9 something accuracy, and if you go with simple static quantization with the same operations, you will never get better than this. Of course, you can remove operators in static quantization to gain again more accuracy and lose some latency, but at the end you have more latency gains with the few static quantized operators. So it's really again experimenting and finding what fits for your solution. And since we only have around 15 minutes left and to answer a few more questions at the end, the notebook is also in the repository Louis has shown, and a lot of the steps are quite similar to dynamic quantization. So again, in the beginning, we are installing Optimum with our Onyx runtime feature. We installing Evaluate and the evaluator and scikit-learn for calculating the accuracy. And then similar to Louis, we are exporting our model to our Onyx path. And then we are configuring our quantizer and quantization configuration.
Could we zoom in a little bit, Philipp? Sorry.
Oh, sorry, a bit bigger?
Yeah, a little bit.
Sure. Should be good now. Okay.
Yeah, that's good. Thanks.
Okay. And compared to Louis, we are not having static faults and per channel faults. So we really want to statically quantize our model and for each tensor, meaning that we are like potentially splitting out operators into like their like lowest number and then doing the quantization of them and having at the end potentially more operators in our graph, but all of them are quantized. So if you are interested in it, you can like take a look at the graph before doing quantization, and then like at the graph after quantization with static, you should potentially see more operators, like low-level operators, than like those combined or fused operators. We are also like adding the operators we would want like to quantize. In this case, we're going with matmul and add. And here you could also add, for example, relu if you would like to add. And those operators you can add here are the ones supported by Onyx Runtime, and they can be found in the documentation. And then also like some additional configuration that we would like to use. Key operators is needed since we are like doing this per channel quantization, and also the linear ops. We can create our config and our quantizer, and then compared to dynamic quantization, where we would now export our model, we need to do this calibration. And for calibration is basically we are having our data set, or a data set which the model is fine-tuned on, or which we would like to use to calibrate those ranges we are like later using for quantization. And what we are basically trying to do is finding the best fit. So we are loading our data set with the quantizer get calibration data set. Here again, we are using the data set ID, which is the banking 77. We are providing a processing function, since to feed something into our model, we need to like process this human readable string to our inputs, which our model can understand. Therefore, we have this simple tokenized function. You might be familiar when fine-tuning transformer models. And then we provide a number of samples, meaning how many of our like whole set of data set are we going to use for the calibration. And in this case, we are going to use 265. And the more samples you use, of course, the more time it takes, and potentially the better the results are, because then like those samples are more diverse. So if you have like a data set of 1000 and like each 100 samples are completely different, then you should like set a pretty high calibration sample. And then we are going to use the training set of the banking 77 to just because we only have a test that we would like to use for inference later. And then similar to quantization, for calibration, we have a calibration config, which allows us to use different static quantization method, like min, max, or in this case, percentile. There is also a good paper linked inside the notebook where they analyzed, okay, which calibration methods work best with different architectures. And for bird-like models, percentiles work the best or better than min, max, or other strategies. And for like initializing our configuration, we need our data set and then our percentile. And this number might look a bit weird to you. This number was created by running hyperparameter search on the percentile. So what we have did in advance is to basically use Optuna and then a different set of percentiles from 99 to 99.9999, meaning like 4 nines, and to find the best percentile, which gives us the best accuracy. And that's really what makes static quantization way slower and way more like compute intensive than dynamic quantization, because we need to find this percentile, which is used to calculate the ranges to give like the best results at the end. And for this, it's like even worse than like for a learning rate. It's really like not at all like, so for example, for like a different model or different data set, the percentile could easily be just 99 or 99.4 or something. So it isn't like really a rule one fits all, and you really need to invest in those like experiments to find the correct percentile to get the best accuracy performance. So, I mean, if we have time, we can like test it to change the percentile, and it could easily go our accuracy from 92 to like 30 or something, because like the numbers are so much screwed up that the results are just bad. But since we have done this already, we can use the percentile. And then what we are going to use is like to like distribute our quantization to make it a bit faster using charts. And then like the partial fit. The partial fit is similar to the partial fit from scikit-learn, you might know, meaning that we are like splitting up our data set into different charts and running them. And then we are just providing our vanilla model, our operators we want to quantize, and our calibration configuration. And at the end, we get some ranges we can then like pass into our quantizer, which will run the static quantization. Okay, this is now going to take around 2 to 3 minutes. Maybe we can answer some questions in the meantime.
Maybe just a point before we look at a question is one of the things that's cool about the calibration dataset reader is that it integrates with the hub. So if you've got like your dataset on the hub and the model, then it kind of just works seamlessly. You don't have to do any sort of annoying data processing. There's a question from Nabila, which is, do you guys have any benchmarks across CPU instances of AWS? Or can you comment and suggest what machines we should be looking for? ARM-based AWS Graviton 2 processors are recommended compute for AWS?
So we haven't had done like any benchmarking for Optimum yet. What we have done for Infinity is comparing Intel CPUs, and the latest CPU architecture from Intel is currently Ice Lake, which is also used in the instance type we use with C6i, and we compared it to C5, which is the Cascade Lake instance. And there we have seen up to 20-25 better latency on Ice Lake than on Cascade Lake. And definitely recommended is to go if like on AWS, and if Ice Lake instances are available in your region, to go with them, since they're like cost the same as Cascade Lake and provide better performance out of the box. So it's basically a no-brainer to go with Ice Lake based instances if you have the option. And then for ARM-based instances, I think also like Graviton 3 now got released, like the C7G instances. We sadly haven't tested yet, but they definitely promise good results, but we like have no insights on how good the performance would be with Onyx runtime. That's something you might need to try out, but with the example or the notebook Lewis has shown, it should be possible. Instead of like using the quantization config for the Intel CPU architectures, you can go with the ARM-based one, and then you should be able to run the same notebook if you have installed Onyx runtime. I think like Onyx runtime is currently not offering like those PyT wheels for ARM-based machines, so you would need to like compile Onyx runtime and then install it on the ARM instance and then install Optimum. I think that's like the only most difficult step to use Optimum with Onyx runtime on ARM. Okay, while we were speaking, our calibration was done, and then like really for like this hyperparameter optimization, what we have done is like the seller executed just like a few hundred times to find like the best percentile to use. And now we have our like nice ranges. We can also like use the export method. In addition to the export method, we have created a utility function for the quantization preprocessor, which basically blocks a few quantization operators. So currently we said that we want to quantize all matmul and add operators. And in this quantization processor, which is included in Optimum, we make sure that we are like not quantizing all of them, because we have found out that if certain operators come behind each other or before each other, we lose some performance when quantizing them. So that's basically what we do here. And then we export it similar to what Onyx Lewis has shown with our Onyx model, our new Onyx model, and then our ranges with our configuration and processor. And if we run it, we get also our quantized model. And then we can also like compare the sizes, pretty similar to what we have seen by dynamic quantization. Then to run inference, same story as before, use the ORT model for sequence classification with our new model quantized, and then evaluate performance. And here we should see the first difference compared to what we have seen for dynamic quantization, that we are not getting the 92.4% accuracy. We should get 92.24, which is slightly worse. This can definitely be increased by maybe running a few more runs or experiments to find a better percentile. We did around 100 trial to find the percentile, which took around 2 hours or something. So it really depends on how much time and compute you want to invest to get the best performance. And those 92.24 is 99.7% accuracy of the original model, which is still pretty good in my eyes. And then we can run the same latency or benchmark check where we should see that we are not getting only 1.9% or almost 2% better latency. We might get up to 3 or 2.8, depending on the model architecture, which is like an additional magnitude for faster performance. And then it might be worth to invest like 2-3 hours or finding the right percentile to then have like at the end even like another like magnitude faster model. Okay, this time it wasn't that great. Maybe we can like rerun it again. Model to use in production, especially when you have a lot of load, and want to like get the best performance and the cost-effective performance out of it. And yeah, like steps 7 and 8, similar to what Lewis has shown, we are pushing our model to the hub and then can reuse it on a different instance or maybe in our preferred compute environment. Yes, okay, at least we have now seen that we are like currently at 2.26, and really like to get like the best performance, we probably would need to pin the CPU cores and run the benchmark over a longer period. And then we should see those 2.8% accuracy gains. Awesome. So are there any last questions we should answer or you would like to know about?
German precision on time. Yeah, so thank you to everyone for joining us. If you like what you saw, please give the repo a star and give it a try. And if you have any issues or questions, please open up on the repo, and we'll be happy to take it there.
Thank you.
Great. So I think with that, it's now 5:30. Shall we call it a day? Time for a beer.
Okay, I think we cannot stop. Yeah, thanks everyone for coming. I think the session is going to be was recorded, so if you want to like rewatch it later, it should be available hopefully soon. And if you have more questions like this or like our forum or like Twitter, LinkedIn, wherever, like send us a message and we are more than happy to help.
Exactly, and not done. I'm just going to put a link to where the repo is, where we did the notebooks again, just for those who missed it. Cool. Catch you later.